In 1945, at Los Alamos, a small sphere of plutonium was finished for one job: to serve as the heart of a nuclear weapon. It carried an odd promise: huge power from something you could hold. But the war ended before it was used. The object did not stop being valuable. It changed roles from weapon part to research tool, because scientists still needed to understand what it really did at the edge of a chain reaction. They focused on a concept called criticality. It meant the point where the material sustained a nuclear chain reaction all by itself. Below that line, the reaction faded. Cross it, and it grew fast. The problem was that criticality depended on tiny changes: distance, shape, nearby materials. So the fastest way to learn seemed simple: bring the plutonium close to that line, watch what happened, and pull it back before it went too far. That approach created a culture of hands-on testing, built on confidence and speed. Experiments relied on improvised setups and direct human control, not machines. People worked close to the core, often with minimal shielding, because the danger was invisible and the goal felt urgent. Each test became a balance between knowledge and exposure, and the closer they pushed toward critical, the smaller the margin for error became. After the war ended, the plutonium core no longer sat on a deadline for combat. It became a test object, assigned to a new mission: measure how close it could get to a self-sustaining chain reaction, and what it took to push it over. Scientists treated criticality like a knob they could turn. They brought the core near the threshold again and again, because the data mattered and the pressure to learn stayed high. To do it, they surrounded the core with materials that bounced neutrons back into it, making it act more reactive without adding any more plutonium. These reflectors were often improvised and moved by hand. With minimal shielding, the experimenters depended on careful positioning, fast reactions, and simple instruments to tell them when they were getting too close. The work succeeded when nothing happened. The danger came from how small the margin was. Over time, this approach stopped feeling like a special test and started feeling like routine. The core was repeatedly nudged toward critical and pulled back, as if the team could always catch the moment before it went too far. Around this specific sphere, the practice earned a nickname: tickling the dragon's tail. It captured the mindset perfectly, provoking something powerful on purpose, trusting skill and habit to keep it from biting. In August 1945, Harry Daghlian worked late, running one of those reflector tests that crept up on criticality step by step. He stacked dense blocks around the plutonium core, knowing each piece bounced more neutrons back in. The margin for error stayed thin. That night, he did it alone. One more block went in place, and the balance tipped past the line. The change happened instantly. A sharp blue flash appeared at the core, and Daghlian felt a sudden wave of heat, like a burn from the inside out. The core had gone supercritical, multiplying neutrons faster than the setup could safely handle. He reacted on instinct, knocking the block away and breaking the chain, but the burst had already happened. In those seconds, invisible radiation poured into his body at close range. It was the first time this particular core delivered a truly serious dose to a human being. There was no protective wall between him and the source, no distance, no time to spare. He had stopped the reaction, but he carried the exposure with him. The danger had turned real. In the days after the accident, Daghlian did not recover. His skin and blood began to fail in the way doctors later learned to recognize as acute radiation syndrome. At first, there were brief hopes that rest and treatment might steady him, but the dose he absorbed near the core kept unfolding inside his body. Hour by hour, week by week, the initial flash passed quickly. The damage did not. As his condition worsened, his co-workers did what scientists always did after a disaster. They tried to measure it. They reconstructed the setup step by step and checked how the reflector pieces changed the core's behavior. They looked at timing, distance, and the moment the experiment slipped out of control. The goal was not only to understand what happened to Daghlian, it was to understand how close they all had been. Daghlian died weeks later, and the lab faced a new kind of fact. A single mistake could be fatal, even without an explosion. The first official concern followed, along with internal discussions about safer procedures and tighter rules. But the work did not stop. Experiments continued because the pressure to learn and to produce remained. Now, though, that pressure carried a body count, and everyone knew it. Early 1946 arrived with an uncomfortable truth at Los Alamos. A man had died, and the work still moved forward. The same plutonium core stayed in circulation, treated less like a warning sign and more like an essential tool. Hands-on demonstrations continued, aimed at teaching how close a system could come to critical. The core kept getting carried from one setup to the next. That decision mattered. There were changes, but they were small and uneven. People paid more attention to who was in the room. Some steps got written down. More observers stood back, and a few limits were discussed before experiments began. But the experiments still depended on human judgment at arm's length from a lethal threshold. The lesson taken from the first accident did not end the practice. It only tried to tame it. Underneath those tweaks, the culture stayed the same. Confidence, speed, and a belief that skill could outrun physics. Near-critical work remained a kind of performance as much as a measurement, and the core kept serving as proof that experts could control danger in real time. Each successful run reinforced that idea, and each repetition quietly raised the stakes because the core did not remember the last near miss. In May 1946, Slotin ran a demonstration that showed how easily a plutonium core could be pushed to the edge. Instead of stacking reflector blocks around it, he used two beryllium hemispheres, like a clamshell, that surrounded the core and bounced neutrons back in. The only thing keeping that shell from fully closing was a simple screwdriver held by hand. It was controlled by fingertip. The idea sounded straightforward. Lower the top hemisphere, watch the instruments, and stop just before the system became self-sustaining. But this setup punished tiny errors. With separate blocks, changes happened in steps, and the reflector never wrapped perfectly around the core. With the beryllium shell, each millimeter of closing made the reflection stronger and more complete. Near the end, the margin between safe and lethal shrank to almost nothing. That was why the screwdriver mattered so much. It acted as a spacer holding a small gap that let neutrons escape, and Slotin varied that gap to show the approach to critical. Yet it also meant the entire experiment depended on a tool that could twist, slip, or be bumped. The closer the hemispheres came, the faster the reactivity climbed. This method did not just flirt with criticality, it balanced on it. The screwdriver slipped. In that instant, the two beryllium hemispheres closed farther than they ever should have, and the plutonium core jumped into a prompt critical state. The reaction surged, not gradually, but all at once. A sharp burst of radiation flooded the space and reached every person by simple proximity. The demonstration became an accident before anyone could think through what was happening. Slotin reacted on instinct. He forced the top hemisphere away, breaking the geometry that kept the chain reaction feeding itself. That single movement stopped the spike, but it came too late to prevent the dose. He took the brunt at the center, closest to the core, and directly over it. The others received less, but they still absorbed radiation in a fraction of a second. Immediate triage started with the simplest question: who was where? Positions around the table mattered because distance and shielding were the only protection anyone had. The group separated, names were recorded, and exposure estimates began right away. Slotin, known to have been closest, became the priority case, monitored for early symptoms. The rest were assessed in order of proximity, then sent for measurement and observation. In the days after the burst, Louis Slotin's body failed in stages, the way a severe radiation dose often worked. The early sickness did not pass. It deepened. Doctors recorded everything they could because there had been no playbook for an exposure like this in a healthy adult who had walked in and then suddenly started breaking down. After 9 days, Slotin died. The lab had lost a second man to the same piece of plutonium. The people who stood in the room did not share one outcome, but none of them walked away untouched. Their positions around the core got turned into numbers. Who stood closest? Who sat farther back? Who leaned in? Those estimates followed them for years, then decades, as medical checks looked for patterns in blood changes, cataracts, fertility problems, and cancer. The accident became more than a tragedy. It became a long-running human study that no one had agreed to join. Inside the institution, the meaning of the accident shifted fast. The split-second act that stopped the reaction had been brave, but it had also revealed the real failure. The work had depended on a hand, a tool, and perfect luck. That was not a safety system. After 2 fatal doses, the informal culture of close-in criticality work no longer looked bold or efficient. It looked unacceptable, and it forced a rethink of how this kind of experiment had to be done. After the second fatal accident, the message stopped being theoretical. It became operational. Los Alamos changed how dangerous materials got touched, moved, and tested. Work that once happened inches from bare hands shifted to remote tools, long-handled devices, and rigs that kept people back by default. Physical barriers mattered now. So did distance. The old assumption that skill could replace protection no longer held. Procedures tightened into hard rules. Experiments required written steps, approvals, and trained teams. Not a single expert improvising at the bench. Interlocks and engineered stops prevented parts from closing too far or too fast. Limits were set for how close any setup could approach critical, and instruments watched for warning signs instead of relying on human senses. Monitoring expanded, and records followed exposures with more discipline. The plutonium sphere that earned the name Demon Core no longer belonged in hand-stacked demonstrations. It was removed from manual criticality work, treated as a hazard to be controlled, not a lesson to be repeated. What stayed was the imprint it left on the field. Distance, shielding, time limits, alarms, and training became standard protections. Its legacy lived on in the rules that made survival routine. By the time the nuclear world reached the present day, criticality safety stopped being a personal skill and became something engineered into the work itself. Facilities treated a chain reaction like a hazard that had to be prevented by design, not by confidence. The goal stayed simple. Keep fissile material from ever reaching the wrong shape, mass, or spacing. That mindset directly answered what happened in 1945 and 1946. In modern labs and fuel cycle plants, the safest criticality experiment often never happened at all. Material moved with remote tools, behind shielding, and under limits that locked in distance and geometry. Containers got built to stay subcritical even when dropped or flooded. Instruments watched for neutron changes, and alarms forced work to stop. Interlocks prevented one more try. The human hand no longer served as the last line of defense. Procedures hardened too. Work required written steps, verified setups, and trained reviews before anything got assembled. Regulators and internal safety groups demanded documented limits, audits, and reporting, so risky improvisation lost its hiding place. Instead of a lone physicist testing the edge, teams controlled each variable and recorded it. That contrast captured the real legacy. The Demon Core's reputation pushed an entire industry towards systems that made repetition unlikely.